When engineers analyze a continuous physical structure, like an aerospace bracket under active load, they hit an immediate mathematical roadblock. To predict how a material will flex or fail, we formulate a boundary value problem. This requires writing differential equations that describe the physical behavior across every microscopic point of the domain. For simple textbook shapes, we can find exact analytical solutions to these equations, but for complex geometries, an exact solution is often impossible to find. Instead, we must rely on numerical approximations. This necessity led to the finite element method, or FEM. While modern engineers interact with FEM through software interfaces, the method itself is strictly a mathematical framework. FEM operates as an implementation of the weighted residual method. Because our numerical approximation isn't perfect, plugging it into the original differential equation leaves a residual, a leftover error that isn't quite zero. The Galerkin method provides a mathematical strategy for handling this error. It ensures the weighted average of this residual is zero across the domain, forcing our approximation to align with the physical behavior of the material. What distinguishes FEM is how we apply this math. Rather than attempting a global solution for the whole structure, we apply the Galerkin method locally across smaller, isolated subdomains. To understand how this works, we will trace the complete mathematical pipeline of FEM, starting with the derivation of a single one-dimensional element and building up to a fully assembled, solvable system. By following this entire local-to-global assembly, engineers can extract precise, actionable data from an otherwise unsolvable continuous reality. The first phase of this pipeline is discretization, taking the continuous geometry and mathematically chopping it into finite pieces. We define these individual geometric subpieces as elements. The specific coordinate endpoints that bound and connect these elements are called nodes. If we isolate a single one-dimensional element, we can assign displacement variables, u1 and u2, to its two nodes. Our objective for this specific subdomain is to derive a localized set of equations that govern the mechanical behavior of just this piece. This mechanical behavior is expressed through a standard matrix equation. Here, K represents the stiffness matrix, U is the vector of nodal displacements, and F is the vector of applied forces. To calculate the values inside that stiffness matrix, the Galerkin method maps the material properties and physical geometry of the element directly into the math. By finalizing this local matrix, we have established a self-contained mathematical rulebook. We now know exactly how this uniform piece of the structure will react to force. But suppose we introduce a physical variation, like a tapered element, where the cross-sectional area decreases from left to right. This change in area complicates the underlying governing differential equation for this specific element. Calculating the stiffness matrix requires integrating shape functions over the element's volume. When that volume varies, hand derivation becomes an arduous task of complex calculus. To bridge this gap, engineers turn to computational tools. Symbolic manipulators, such as the open-source program Maxima, can be used to algebraically integrate these shape functions across the varying geometry. The output of this symbolic manipulation gives us the exact local stiffness matrix for the tapered geometry, ensuring the math remains precise despite the complexity. No matter how complex the local geometry gets, symbolic manipulators allow us to lock down these local equations before moving to the global scale. With the rules for the individual subdomains established, we shift our focus back to the behavior of the complete structure. The response of the whole structure is dictated by connectivity, how these individual subdomains interact at their boundaries. To solve the original boundary value problem, we take the local equations and assemble them into a single global matrix. When two adjacent elements are joined, they connect at a shared center node. A physically shared node implies mathematically shared variables. The displacement at that point must be identical for both elements. When we drop their local matrices into the global grid, they overlap directly in the cell corresponding to that shared coordinate. This overlap represents addition. We are summing the physical stiffness contributions from both elements at that shared boundary. As the third element snaps into place, its matrix drops in, continuing this overlapping sequence down the diagonal. The completed global matrix now serves as a unified numerical map of the structure, housing every local stiffness contribution and every geometric connection within a single coordinate system. Even with the system fully assembled, we encounter a fundamental algebraic obstacle. If we attempt to solve the matrix as it stands, we find its determinant evaluates to 0. This means the matrix is singular and cannot be inverted. Physically, this is because the structure is currently unanchored. If we apply any force, the entire bar will simply float through space in what is known as rigid body motion. To solve this, we apply boundary conditions. By attaching one end of our bar to a rigid wall, we fix the displacement of the first node to 0. Mathematically, this allows us to strike out the corresponding row and column in the global matrix, reducing the system. By anchoring the model to physical reality, we transform an unsolvable floating geometry into a stable algebraic system. With a stable, reduced matrix in hand, we execute a solver algorithm. This produces a vector containing our primary variables. These primary variables give us the nodal displacements. We now know exactly how much each point in our bar has moved. But determining movement is only the first half of the analysis. Those solved displacements are plugged back into our original local element equations to solve for secondary variables, the reaction forces and internal stresses. These discrete numbers are then mapped back onto the geometry, visualizing the continuous physical behavior of the material under load. While we have explored this through a simple one-dimensional bar, the underlying logic remains the same for complex three-dimensional models. This sequence, moving from localized weighted residuals to a global assembled system, is the exact mathematical pipeline that makes modern structural simulation possible.